So this talk is based on the database holography due of the Quark-Gluon plasma, and basically we try to use this talk is application of the AI or application of the deep learning and neural ODE. So I officially I comes from the Ningbo University. We established a fundamental research institute here, and welcome you all guys to visit us. And this talk is based on the collaboration with Professor Ronggen Cai and from the Ningbo University, and also Lily from ITP in Beijing, and my student Fu Qinxuan and Li Yi and Wang Yuanxu and Zheng Hong'an. And so this talk is based on the main based on this work, and also I try to report some recent progress around this direction. And some part of them and already reported in the machine learning student machine learning conference in Yokohama Institute. But here I try to explore something more. And the outline of this talk is firstly, I will introduce the basic motivation and what is my personal motivation, try to do, apply AI or apply machine learning to try to construct the so-called the holography model. And this is promote us to, this technique to promote us to build up some so-called the data-based holography model. And the most important part for QCD matter is Quark-Gluon plasma. Sorry, there are some more sensitive. And the third part, I will focus on the equation of state, so-called the EOS and the hydrogen property of for the QCD matter. And finally, I will give a summary. And this is something new, new part in this talk. So the motivation is that try to understand the schematic view of the QCD phase diagram. As you know, and in the QCD literature, and people try to study the phase of the QCD matter in terms of the temperature and also pion number chemical potential. And there is a schematic graph for this QCD phase diagram, but this is almost all this solid part is found by this one and also for this one. And for the y-axis and x-axis. Between the QCD matter, between this one, and there is a so-called the phase boundary between the hadron gas and Quark-Gluon plasma. And there is a exotic theoretical people in phenomenological QCD literature, they suspect that there is some exotic phase, so-called the color flavor locked phase, which is so-called the color superconductivity phase. And in this talk, we are mainly focus on this part and this part. And there is must be some first order phase transition. It's just expected in the literature in phenomenological or effective field theory and first principle calculations. It's just expected, but now there is low. There are few effective model to try to understand to clearly to understand what happened for this hadron gas and Quark-Gluon plasma. And so this is, but and here we try the talk were based on some data. So the data is offered by the latest QCD, and the data are available only for this axis, for only for y-axis. Lemni is just a bio number chemical potential to be vanished, and there is numeric data and also some experimental data around their switching. And we try to use this data, try to extrapolate the model to be describe the Quark-Gluon plasma phase. Usually, the Quark-Gluon plasma in that region is free. Is usually regarded as the ideal fluid phase. And the two main properties. One microscopic property is equation of state for the Quark-Gluon plasma, and also for the hydrogen property for the Quark-Gluon plasma. And for all previously for all type of this attempt to try to describe this one is people try to build up this holography model to mimic or con quantitatively to describe this quark-gluon plasma, the main property or microscopic property for the quark-gluon plasma. They our in this talk we are mainly build to try to combine this equation of state and hydron properties. This is the most two essential character of this character of this quark-gluon plasma. And so why is this is important? Why this quark-gluon plasma property is very important? Typically for this regime for high temperature and high bion density region. In that region, and the is a strong coupled QCD system, and usually we don't not for strong coupled quantum field theory. There is no systematic way to try to do that, but they can use some non-perturbable theoretical approach. And once there is a first principle calculation, usually it's called by the latest QCD people, and there is a famous sign problem because once you turn on this fermionic degree freedom, and the latest QCD can only attach the Bayer number chemical potential to be one-ish. So in that sense, we can there is due to the sign problem, the first principle calculation does not reach the quark-gluon plasma regime. And also, so for the non-perturbable effective field theory or effective model, the famous one is so-called the Schwinger-Dyson equation. But this one will be highly sensitive to the truncation dependence and non-uniqueness. So that in that sense, you have to build up. You have to include more degree freedom, but such more high energy mode of the degree freedom come into the Dyson-Schwinger equation. The final result will, or the phase diagram will be highly changed. And so another approach is usually we call the Lam-Goto NGL model or P-NGL model. This model is a model dependence and a low confinement and the low gauge degree freedom. So in that sense, there's some topological non-perturbable topological effect will be missing in this model. And also, it's highly dependent on the model and model parameter. And you have to match the data, and you have to realistic data or the first principle data, calculation data. You have to fine tune the model parameter, and you have to set up this model. But there is no systematic way. And also for the functional renormalization group, this is also depend on you have to make a truncation and you can meet with the sign problem. And all this model, all there is no unique or unified model or unified theoretical non-perturbable approach. So we can attach just some aspect of this QCD phase diagram, typically for the quark-gluon plasma phase. And we try in this model, we try to in this work we will try to apply the ADS-FT to try to understand the QCD. But you know that the QCD is highly different from the conformal field theory, and the ADS-FT and there are several big gap between the ADS-FT and the ADS-QCD. For example, the first one is highly for typically for the ADS-574. This is the n equal 4 super Yaml theory. This is a highly supersymmetric theory. But for our QCD is long supersymmetry. And also for the color degree freedom in the typically solid in the ADS-FT, ADS-574 is fit good well and the large capital N. N is associated with color degree freedom. But for the realistic QCD, we only have a three color. And for the safety side, because all this matter field associated with represented is the bi or joint representation. But our realistic QCD, some quark is belong to the fundamental representation. So we have to care about the so-called chiral symmetry breaking. And in realistic QCD, you know that the quark has mass, so chiral symmetry will be explicitly broken. So and also low conformal symmetry. And for the n equal 4, there is a highly, this is maximal superconformal field theory. And for the QCD, there's low conformal. And as we know that the gauge coupling satisfies the so-called asymptotic free property. And so for ADS 574, and there is a so-called the standard well-established gravitational dual theory. But for the QCD, there are several people just almost 10 years ago and almost 10, 15 or 20 years ago, and people try to understand, try to build up the bottom-up and top-down model to mimic a QCD property. Typically for the Rak-Kyeong QCD phase diagram, the first paper to study QCD phase diagram is proposed by the Gapser, and follow up the several paper, and up to now, and we don't have quantitative description for the for fully understood the Quark-Gluon plasma typically. So this talk is main try to use AI or try to use a new, because we have a strong power AI power to apply this AI, try to understand the or to try to build up reasonable and quantitatively so-called the ADS QCD model. And how to build up this, as we know that the QCD phase diagram, and we know the gauge coupling for the QCD with respect to the energy scale, and you can see that in the higher energy region is correspond to the asymptotic free, and for the low energy region is correspond to high non-perturbative region. So in this sense, we have to in terms of the two, typically in this talk we are typically focus on the 2+1 flavored QCD data. This data is offered by the latest data and also experimental data. We try to combine this data, try to build up this quantitatively holographic QCD model. So that's why in this talk we call that is a data-based holography model. To mimic the QCD phase diagram, as we know that there is a Quark-Gluon plasma, this is a hadron gas. And there is also a first order phase transition, and this is the endpoint for the first order boundary, first order phase transition boundary. And we need two important ingredient. One is the temperature, and our other is the bion number chemical potential. And also, we have to know that the realistic QCD there is asymptotic free, and we have to broken the conformal symmetry. So we have to turn on this conformal some scalar field. This is the effective scalar field, background field. The scalar field will turn on some sources. This source with some energy scale. So in that sense, we can explicitly broken the conformal symmetry, and also you can find in the holography side, we need some bio number chemical potential. So in that sense, we have to preserve all the QCD process will preserve the bio number conservation property. And also we need a temperature. In the gravitational side or in the effective holography bottom-up approach, and we need a black hole solution, because a black hole solution will be naturally induce the temperature. This is our main ingredients in this model. And but there is a problem is that we have no idea what is the Z phi and V phi. This is a functional, because this Z is a coupling between the phi field and with a bion chemical potential. And the non-trivial V phi will be determined by this by data in terms of the equation of state, because we only have a microscopic data, and we can, in terms of this data, in terms of the equation of state and of also hydron property, how can we combine them to precisely determine this unknown function or unknown functional? Usually you apply the AI or neural ODE to extract this. We can guess, so we can put some form of this function and try to determine the coefficient. But right now we have no idea. We try to systematically build up the algorithm to try to in terms of the data and combine this data, and we can work out the functional. It's not function. So it's not the data, it's not the parameter fitting. It's just to extract the model, extract the numerical model. But this is a functional. So there are two functional. We are to precisely determine that this guy will be. We have to highly depend on the data because there is no principle, guiding principle to tell you. We just know roughly this model structure, but we have no concise the structure for this Z-Phi and V-Phi. This is a phenomenological, and we have to much more close, highly sensitive to the data. So we have to choose the proper data to determine the Z-Phi and V-Phi use a following algorithm I will introduce in the following slides. And but the essential you know that this guy and this guy will be infinity dimensional or it's look like a needle in the ocean. There are many you can define some so-called loss function and to use some so-called optimization procedure to try to find the minimum to feed the data to find and inversely we can determine this one. And what we can do is that we just build up in this paper we just build up this algorithm. Try to this is a generic algorithm. We have no idea Z-Phi and V-Phi. Typically, we can here. I just show simple example as we just want to determine the so-called Z-Phi. And we just try to build up in terms of the holographic QCD and in terms of the ADS-FT. We try to build up the asymptotic ADS background, ADS black hole background, and because we have no idea, we know the Einstein equation. There are several in the holographic QCD. To derive this action, there are several ways, but that's now we just focus on the neural OD because it's quite sensitive to the once you if you want to realistically work out the QCD data and you have to compare with QCD data, realistic QCD data, and you can find some matching or some data fitting, and you were in a, close to the UV boundary region and it's very high, it's highly sensitive. We need a highly precision data, highly precision numerical simulation. And what we can do, we can implement this they instead of this they high they had find this is a functional or Wi-Fi whatever you type of this unknown functional. And we can once we know this roughly the holographic structure of this holographic the global structure of this holographic model, and we just implement replace this unknown functional with respect to the with some neural network. This is a neural network. We just use a phi and this is the phi, and to instead of this, we put this guy embedded into the Einstein equation, and then we try to use the holographic dictionary to work out the near close to the UV boundary data. For example, yeah, pressure or entropy or some physical observable or quark condensation, etc. And we combine all complete data set as complete as possible, and then we compare with all realistic data with and compare with realistic data and also holography prediction. And then we define this difference description between the holographic prescription and latest realistic QCD data. And we can define the so-called the loss function. And all this uh, neural network will depend on some load. Some load. This load is highly is parameterized by the size so-called the parameter or functional space. And then we can use some add-on or some optimization of process to make the to make sure they minimize this loss, they minimize the loss function, and then to propagate back propagation to update this psi, and then finally you can do the recursively. But essential and finally up to you do use optimization process, and then finally you can determine this z phi or z hat phi or v phi, etc. But the essential point is that, for example, we start from this model. For example, we just here we just you can arbitrarily introduce some coupling. This is a so-called magnetic coupling. This is a but with coupling with a bound number accessibility, bound number conservation constraint. And you can work out in terms write down the standard Einstein equation in terms of this following answers. And you can find the standard solution from the horizon to the boundary. And the horizon, you can input some parameter. This parameter will be, you can solve this equation of motion, but this is a neutral ordinary differential equation. Usually we, all the equations, all the unknown functions is depend on the R direction or so-called holography direction. And we can work out the boundary, prescribe some boundary data, for example, entropy, etc. This is so-called the equation of state. And and then back propagate this compare with data, realistic data to finally to determine this Z phi, V phi, and Z hat phi. And here we just show how can we realize, because this is a second order differential, ordinary differential equation we can writing as a fourth order, rewriting as a fourth order phase differential equation. And we try to solve this Einstein equation coupled with matter field, and then we can solve this start from the horizon and to the boundary. And then try to work out the mu b and magnetic field, for example, entropy and pressure, etc. And this physical quantity can be compared with the latest data, and then the difference or description between them and is so-called the so-called loss function. And then we just we need this data and to minimize this loss function, and then to try to determine this so-called z hat phi, for
So
example.
I
This
have a
is
question. I mean, the input training data are like vectors of numbers, or what is, how does the training data look like?
this data is a number, is like is two-dimensional data. For example, there is a for example, there is a so-called this example. For example, for entropy, and there is a curve. There is a band curve. Sorry, this is band curve. The band curve is extract the latest data, and but they have some systematic error bar, and we solve this Einstein equation to predict the holography predict entropy, and compare this entropy with the realistic QCD entropy, and then we can match. We try to minimize this two different data. This data is one. This is two. For example, in this case, we offer some four independent thermodynamic quantity. For example, entropy, magnetic field, and also pressure and Bayer number susceptibility. And this data is just two-dimensional. And for each data, we can firstly we just do the global fitting between this. But for each data set, for example, for entropy and pressure, each data to define the loss function, we have to introduce some for entropy. We have to introduce some so-called the probability for entropy in the whole data, and also for the pressure, and combine all of them and unify this unify the four different data set. And but this is the independent This is an independent thermodynamic property. So once we determine the four guys and all the thermodynamic quantity were exact consistent with latest simulation, etc. So could I?
Yeah, continue.
Yeah. Thanks. So we just use this algorithm and then to try to determine the so-called whatever the hard file or wave file or once you want to introduce a new physical phenomena of new, you have to introduce a new degree of freedom. But as I said that there is no, for example, there is no guiding principle to tell you what type of this, no, what type of this. And here for typical example for 2+1 flavored QCD system. And we can work out, we just use this algorithm to read out this one. And previously we guess this one and we just use machine learning to extract this, this is some so-called the seed solution. This is use this such type of roughly you can get some seed solution, and once we can work around this random work around this seed around the seed, and then you can generate some new solution or new better solution, and then we just use the AI or previous machine learning approach try to extract this analytic solution. And then this solution is finally we this is a, minimal solution which is contains the almost eight of late 1, 2, 3, 4, 5 uh, 8 parameter to exact determine this model. And this model, what type of this, what are the, you can see this data, we just we just do the global fitting. The data set is contained, typically for this case, for this case, and there is data for the chemical potential, one-ish chemical potential, because one-ish chemical potential can be obtained the latest simulation. We just trust the latest QCD simulation, and the error bar, the point is correspond to the latest simulation, and the holography prediction is given by this holography model. And you see that this we just only apply this 8 parameter to exact determine the, because from you can start from this parameter to map to this such type of this data. This is sound speed and heat capacity, and also for the second order Bion number accessibility. And you can see that the holography model is quite good capture the equation of state. And this is the previous data is just only for the equation of state, but we need a more higher precision data come from the latest QCD, and the latest QCD offer some service data associated with so-called the generalized higher order balance stability. This is based on previous data, latest data extended to the higher precision data. We conclude the higher precision data and to more highly determined to highly precision to determine this holography model. And you see that the holography prediction is quite good or great with latest data. Typically, this is continuous extrapolation from the latest simulation. And you can see that our model is quite good to agree with. This is more high precision data, because this is mostly inside of this so-called the phase transition of the QCD long monotonic behavior. This data is taken from this paper, and but uh, but here we only focus on the Bion number susceptibility to Bion number to be one-ish. So in that sense, in the QCD phase diagram, as I said that at the very beginning, and the data is only from the y-axis. And how can we extend? How can we trust this model? And we have to incorporate the experimental data. And fortunately, there is for finite chemical potential, there is the experimental data extracted from the STAR collaboration group. And this paper and they give us they offer this data, and we just use this. We incorporate in our algorithm. We incorporate this new data and experimental data to do the global fitting, and then finally we can find all this all the holography prediction is consistent with in some sense our holography calculation is quite nice to capture the most important QCD property, non-perturbative QCD property. And so once you build up this holography model, and we can predict the so-called the QCD phase diagram. This is a schematic for QCD diagram. For this region, is already ruled out by the latest simulation, and also for this region. And we predict some so-called the critical endpoint. This is correspond to the first order boundary between the Quark-Gluon plasma and hadron gas. This is the first order phase transition, and we found the first order phase transition between them. And there exists the so-called the endpoint of the first order phase transition. And this prediction is consistent with the Dyson-Schwinger equation and with recent functional renormalization group. And the D6 is the so-called the recent functional Dyson-Schwinger equation, and this is correspond to the functional renormalization group. And also, um, so 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 in that sense, our holographic prediction is quite nice to quite, but there is a problem. How can we go further? Because for Quark-Gluon plasma, for this model is not well defined. Have a just for the hydron property, there is a strange behavior for this model, because hydron property for once you typically you focus on the high so-called hydron property, for example, shear viscosity or bulk viscosity. We will say this model is ill-defined. And what this constraint this comes from this so-called this realistic QCD data. As realistic QCD data, there is a so-called the shear viscosity with over with entropy density. This ratio will be such type of the non-trivial temperature dependent behavior. There is a minimum point around here, but in our previous model, in the literature, that is belong to the all Einstein gravity, and this is Einstein for Einstein gravity is given the eta over s will be given 1 over 4 pi. So there is a highly non-trivial contradiction, because our model tells you that the QGP shear viscosity with shear viscosity such as just a constant share for ratio for the shear viscosity and entropy, the ratio to be 1 over 4 pi. This is the so-called famous KSS bound in the holography literature. It's offered by by Sang and his collaborator. And but the realistic QCD system and the QGP has a highly non-trivial non-monotonic behavior. For example, the eta over s will be decreased with respect to the temperature and increase with temperature after the phase transition point. And also for this so 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 KSS bound is not enough to describe this. So in that sense, our previous model in this model does not don't capture the hydron property, just only for the equation of state. We have to incorporate the hydron property data, and how can we describe, how can we realize use holography model, how to in terms of the holography prescription. And also you can see, because QCD data or KCD matter is highly non-trivial. It's not the same as predictable as a holographic QCD, previous holographic QCD model. So in this sense, previously we just capture the most important equation of state and we have to incorporate the hadron data. So that is the main new sense. And also there is shear viscosity also for the bulk viscosity. We just extract the most Bayes analysis in terms of this effective field theory and also experimental data to uh, uh, to to evaluate this bulk viscosity over shear entropy density. And there is you see that the number is quite small, but the band is also small. And you see that from our previous data, our previous calculation, we show that this we can't capture this most important non-trivial temperature dependent behavior. How can we cook up this model? How can we so in that sense we have to it is very necessary to modify this previous model. The previous model we for example we have this guy. This is the Bion number accessibility associated with the Bion degree freedom, and also for the non-conformal. And how you naively you just if you evaluate the entropy, shear viscosity, and entropy bulk viscosity does not satisfy. Naively we evaluate this in this model, and you cannot obtain or achieve this realistic QCD data. We have to incorporate more data, more processed data. As I said, that this is just only application of this AI or neural ODE to so in that sense, to realize this hadron property of the QCD matter. And here, from the human learning, we learn that with human learning tells you that higher derivative gravity will be change the shear viscosity and bulk viscosity. And naively guess we just introduce so-called Gauss blade. So since the Gauss blade comes from the string theory, it's well defined, and it's well, but there is the phenomenological data. There is a phenomenological coupling between the phi and Gauss blade. There is no guiding principle. As I said, there is no guiding principle. How can we determine this guy? This H phi. There is well, how we just say how can we realize this? This is a work in progress with my student and also Professor Zhonggen Cai and Lili. And previously we have 8 parameter, and we introduce some functional. This is an infinity dimensional space-time parameter space. How can we turn on? We just slightly we just we can turn as a constant or and as a polynomial function for this h phi and the exponential function for h phi arbitrary. There are many combinations. There are infinity possible combination for this for form of this h phi, and we try to use machine learning to optimize this to determine this guy. And finally, we find this combination, and we just only use 8 parameter to see. This is the equation of state. This is equation. We do the global fitting equation of state combined with the hadron data. So the equation state data comes from this guy, and you see that the red lines correspond to this previous model. We just use the 8 parameter. We slightly turn on this model fitting, global model fitting in terms of the neural ODE. And we can find the blue line. The blue line is ADS QCD or holography QCD combined with Gauss blend. And also is you saw in this sense for this there is a previously there is a discrepancy between the data and the model prescription. But there in this once you incorporate the high Gauss blend and this description will become smaller and smaller. So the numerical data, prediction is much improved, highly improved. And so also you can check the sound speed and also current bio stability. This is but this part is only for the equation of state. And the data is the equation state, and you see that is highly. You can also you can also look at this 2+1 flavor and 2 flavor and SU3 pure Gluon system. And here we main sense is we how can we incorporate this uh, hydrogen property of the UNIST QCD data, and here this data is extracted from the Bayes analysis. They have 90% computation to plot this Bayes analysis associated with eta over S, and this band the yellow band lines associated with eta over S, and we just use the data to try to we find this non-trivial non-monotonic behavior. Uh, Once you go the higher order, go to high temperature, they go down and up. So in that sense, this model is captures the shear viscosity, and also how can we how about the bulk viscosity? For bulk viscosity and previously without this the dashed line, this dimensional lines are also associated with without the Gauss blade. And this model to tell you that you need Gauss blade, you need a non-trivial Gauss blade, and you gradually turn on this alpha, and you can find this is the up to the alpha goes to minus 0.005 point, and those you can find this bulk viscosity issue over ratio of the bulk viscosity and entropy density. And you can find the holography model is consistent with the latest Bayes analysis. From the Bayes analysis is taken from this paper, and they basically they comes from the model analysis and also experimental analysis. So in that sense, so far so good. And in this model, convince or try to use this model to convince that AI can help us to build up this quantitative model to describe the data. Is so-called the data-based holography model. And then you can slightly study the phase transition, and you can once you can slightly decrease the bio number chemical potential. You can find that this is a this is so-called the free energy. The free energy shows that the swallowtail behavior. This is a strong insight to tell you this point is correspond to the fourth order phase transition, and gradually uh, decrease this bio number chemical potential, and this behavior will become small and smaller, and finally disappear. This crossover. So in that sense, it's consistent with phenomenological or effective phase expected the QCD phase diagram. There is a phase boundary between the Quark-Gluon plasma and the hadron gas. So that's all I can say today. And so let me briefly summary. And we predict we build up the data-based holography model to try to quantitatively agree with the latest QCD data and also experimental data from the STAR collaboration group. And also we also incorporate the hydron data. And this hydron data is we do the global fitting to make the previous model to be more precise. And that's all I can say. Thanks.